So let's start lecture number 4. Now you may have received your dataset, you've collected the data in the world, you've got it from a colleague or maybe from some other source, you may even have done your data cleanup, you've looked at all the anomalies, you've looked for outliers, you've looked for all the data integrity problems and fixed all of those things. However, even after you have done all that, it may be that the data that you have, even though it's a very good data, it is not in the form where it's susceptible to good modeling. And yet, intrinsic in the data is something that allows good modeling. The gap here that needs to be covered is you need to do feature engineering. It may be that the features in their raw form are good data. You have faith in their integrity, but they are simply not quite the way that they need to be in order to be usable to have predictive or analytic power. That's where we get to this particular lecture. We are going to talk about ways in which you can engineer your feature. These are mechanistic transformations either on individual features or globally on the dataset or on combination of both features that allow it to expose something that is inherently there but it is not easy to see based on the raw features. Obviously, the more dimensional your data is, the more complexity that is contained in the dataset, the more likely this is to be true. Let's first look at a simple artificial synthetic example that makes this point sort of obvious, but it's a good demonstration. So, we are going to import all the required packages at the beginning in cell 1 and then we'll read in our dataset using pandas read CSV. Now, I mentioned earlier too, there are some places where particular libraries that we used aren't quite in sync with each other correctly and they tend to issue some warnings. So, we don't need to look at those right now. That just has to do with some particular version of an API that's being deprecated. And it takes a while for one library using another to catch up with that. Now let's come to cell 2 and see how our data looks. The data that you see here has feature underscore 1 and it has feature underscore 2 and it has a target. We haven't given any more descriptive names to those, but that's fine. We imagine that we might want to do some kind of prediction of the target from feature 1 and feature 2. Now we could ask for the correlation matrix. So the idea about correlation matrix is that we find out how well correlated various features are with each other. So in cell 3, we find out correlations. Of course, along the diagonal, feature 1 is perfectly correlated with itself, as is feature 2, and so is the target. But the correlations between each of these individual things, whether it's feature 2 against feature 1 or whether it's target against any of those things, is really quite low. I mean, we get a little bit, but it's around 0.03ish. But there's no linear correlation or not a significant linear correlation among any of these things. So let's move on to cell 4 and we can take a look at a histogram of what is the distribution of each of these things. Of course, the first one is the target, not a feature, but it has a sort of Gaussian bell curve distribution, as do feature 1 and feature 2, which may or may not be informative, but that is the way the data is often expressed to be. In any case, nothing really jumps out here as having outliers or anomalies or anything particular about it. Now let's come to cell 5. We can make a graph to see if we can find any general trends in the data. Other things might jump out if we do kind of a scatter plot of these things. Well, it's not exactly a scatter plot. The x-axis is the different samples, but we don't notice any clear pattern that's going on. I suppose that we can see feature 1 and feature 2 seem a little bit more broadly distributed than the target does, but they all seem to more or less follow a Gaussian distribution as we saw in the histograms. So we'd like to make sense of it. Of course, these may simply have no relation at all, but there is a good chance that there is a relationship. I mean, I'm giving away the game because I constructed it in a way. But let's try a linear regression. Let's see if we can tease out any relationships which we might think exist. So coming to cell 6, we'll import our linear model from the linear regression. And we'll do a train test split. We'll construct our x by dropping the target column, and we'll construct our y as we often do by just selecting the target column. We'll do our train test split in exactly the straightforward way that we've done numerous times before. Now let's construct a linear regression object. Do the fitting against the training set, do the scoring against the test set, and what we see is we find a really terrible score. It's not, well, it's actually negative, but in any case, it's very close to 0. So this may tell us that we want to reject this correlation. We may think, you know what, there's nothing to learn from this. In fact, the target is unrelated to the features that we have. But maybe we shouldn't stop there. Let's try a couple of other linear models. In cell 7, we'll also try out lasso and then we'll try out the ridge. Maybe we have just a little bit of bias in there, and maybe by doing that we can find some correlations. In fact, we don't. The lasso and the ridge, they are not quite identical, but they are all bad. They are not particularly descriptive. L1 and L2 penalty don't help us there. So now let's come to cell 8. So coming to cell 8, now something that does help us, and we have to know to think about this. I of course did because I constructed the dataset, but maybe I want to combine the two features. Now we are not adding any new information here. So here just a note that I am not inventing features in an artificial way, sort of cause it falsely to make predictions. I am just taking simply the features that already exist, that is feature 1 and feature 2, and doing a sort of combination on them. Multiplication is a very typical one, and adding that to the dataset. So here we can see that we have f1 into f2, that is feature 1 into feature 2, and it's a synthetic feature and it's mechanically derived from these features that we already had. Well, now let's try again. We have an extra feature that we managed to synthesize from the existing features. Now in cell 9, we'll do a train test split because of course we've modified our data, and we'll create a new linear regression object, retrain it and retest it. And here we get a score of 1.0 or absolutely perfect. So this is as best as we could possibly do in our regression. Well, the moral here is that obviously this is artificially constructed, and you can see or infer that this was constructed specifically by making the target identical to the multiplication of those two features. But we can see that there was sort of this inherent implicit information in the data, but it wasn't revealed just by looking at the features as they were presented. Now obviously in some real world example, it's not gonna be as simple as that. It's not that the target is going to be the multiplication of those two features, but often if you have sort of the target represents, at least to some degree, a combination of couple of things that you can directly measure, then that can be exposed. And often multiplication is a way to get at that. Obviously, there are other kinds of combinations of two features that there could be mathematically, but it turns out that multiplication is a pretty generic way of combining things. And it may not be exactly optimal, but if there is a trend, you are probably going to reveal it. Well, we might ask in fairness that we should consider not just linear regressors, but other regressors too. It is possible that we are biasing it by only looking at linear regression, which we know has these certain blind spots to it. So let's take a look at a couple of more regressors in cell 11 and cell 12 and see that if they manage to solve the problem for us without having to engineer the feature. So here again, then we separate our features and target variable, and we are doing the train test split again, and then we are going to do the train test split. So now let's see how the decision tree regressor does based on this data. And so you can see that we haven't engineered a feature here, and it turns out that it actually does quite well. So it's not a perfect one, but it's close to 0.99, so it's almost a 1, and it does certainly much better than linear regression when it gave us a 0. So now let's see similarly how a support vector regression does. So it's not always the case that every regressor is going to fail if a linear regressor can't, or if one particular approach can't identify the data from the raw features themselves without engineering. But we did engineer that blind spot to linear regression specifically. And we can see that the SVM also performs really good. It gives us 0.97. So we see here that if we were to construct other examples, it's certainly possible that these other regressors would have their own blind spots and would benefit from engineering features in some way. In general, adding more features, as long as they are not so many to overwhelm the computational tractability of the problem, they only help. It's not typically going to hurt you, and although we'll discuss this issue below, so pretty soon we are going to talk about a particular kind of feature engineering that is somewhat special, and this particular concept is called dimensionality reduction. It's kind of a global feature engineering. But first, let's see what is feature engineering. So we are going to learn some of the basics regarding feature engineering, and in the next few minutes we'll dive into the implementation. So I would describe feature engineering as a process of transforming raw data into features that better represent the underlying signal to be fed into a machine learning model, resulting in improved model accuracy on unseen data. Again, we care about the model's ability to generalize to data that it has not seen before. It's important to understand just how messy real-world data can be. There's a story in almost all data, and feature engineering is about teasing out that story. It is about taking that mess and funneling it or transforming it in a way to create something that is clean and understood by a machine learning algorithm. For instance, you could tell me a story about a fraudulent credit card transaction that makes perfect sense to me, and I'll recognize it as a transaction that should not be allowed to go through. Of course, it probably took you a couple of minutes to tell me about it, and you told me about it after it had already happened. The challenge is that no human being can review every single credit card transaction in real time. Luckily, automated algorithms or machine learning models can do that for us. So the challenge is taking that story you told me about fraudulent transactions and representing that story cleanly in data for a machine learning model to pick up on. And that's what this lecture is going to be all about. Now, previously, we looked at a machine learning pipeline and it looked like a nice, clean, linear process. The reality is, it's a little less clean and a little less linear. What often happens is you'll pull your raw data, you'll explore that data, clean it, create new features, and you'll fit a model on top of it. And maybe you'll evaluate your model and it's not that great. So then you go back and you transform one of your features and then you refit the model. Then maybe you evaluate that model and it's not that great. So you go back and you transform one of your features. Then you refit the model and evaluate it again to see if the new transformed feature improved the model at all. Then maybe you circle back and you drop a feature that doesn't appear to be providing any signal to the model. Then fit and re-evaluate it again. The reality is, most of the time, you don't really know how valuable a feature is until you've tested it out in a model. So this more iterative cycle is what the development of a machine learning model typically looks like in practice. So now let's dive into more information about why feature engineering matters so much. Feature engineering, well, may be the unsung hero of machine learning. Massive amounts of data and state-of-art algorithms get all the attention, while feature engineering sits in the shadows. Here's a quote from a physicist and a blogger, Scott Laughlin, in a blog post from a few years ago that I think hits the nail on the head. Feature engineering is another topic which doesn't seem to merit any review papers or books, or even chapters in books. But it is absolutely vital to machine learning success. Sometimes the features are obvious, sometimes not. Much of the success of machine learning is actually success in engineering features that a learner can understand. and when he refers to a learner, he is referring to a machine learning model. In other words, we need to engineer features that allow the machine learning model to pick up on the signal in the data. There is a popular phrase that can be applied to many processes, and it holds true in machine learning: garbage in and garbage out. A great manufacturing pipeline cannot cover up low quality materials. A top notch chef cannot overcome low quality ingredients, and a state of the art machine learning algorithm cannot cover up for poor features. In other words, the quality of information coming out of the process cannot be better than the quality of information that went in. Put another way, the quality of features we feed a model is the prime limiting factor on the performance of the model. You can have a lot of data and an incredible algorithm, but with poorly defined features, your model will perform poorly. Better features help us in a number of ways that may not be immediately obvious. First, they give us more flexibility. With great features, your algorithm choice and hyperparameter tuning becomes less important. We can select a suboptimal algorithm and hyperparameters and still end up with a really good model. With poor features, you don't have that luxury. Another benefit is they allow for simple models. With great features, you don't need a super complex algorithm to parse out every ounce of value in the features. With really good features, even a simple model can be quite powerful. Again, complex state of the art algorithms get the attention, but simple models are easier to understand, easier to debug, easier to optimize, and often run much faster than their state of the art counterparts. When you're trying to run a model on something like every single credit card transaction, the ability of a model to run even a couple of milliseconds faster is a huge win. Then there's the obvious: better features mean better results. So now we've explored that what feature engineering is and why it matters. Next, we'll get into the nuts and bolts and we'll figure out what tools we actually have in our feature engineering toolbox. So let's talk about some of the tools that we have in our feature engineering toolbox. We'll start with something that again you won't often read about in academic papers or textbook, and that's common sense and domain expertise. Many times, this is actually the most powerful tool we have. In other words, take a step back and think about the factors you would expect to influence in whatever you're trying to predict. As a very simple example, in fraud detection, maybe if a credit card is used in a country that it's never been used before at a time of day that it's never been used before, then maybe it's more likely to be a fraud. You should make sure those features are in your model. On the flip side, the date of birth of the cardholder probably is not relevant to whether it's a fraudulent transaction or not. Don't distract your models from the things it should be focusing on. Get rid of the irrelevant features. Given a set of features you think are relevant in helping the model pick up on the signal in the data, you need to clean those features to make sure the model can actually see the signal. For instance, you can impute missing values. You could remove outliers so that the model doesn't go chasing data points that are not representative of the underlying trends in the data. By definition, outliers are not representative of the trends in the data, so get rid of them. Another way to clean your existing features is if they are on different scales. Think like measuring something in centimeters versus meters. It can be very helpful to scale your data or normalize your data so that all features are on the same scale. Lastly, similar to outliers, if you have skewed data, the model might go chasing the long tail on your distribution instead of focusing on the actual underlying trends in the data. We can transform skewed features to make it a more compact, easily understood distribution. Another tool is combining two features into one where it makes more sense. Quality trumps quantity every single time when it comes to features. Or on the other side, maybe you have one feature that's not really valuable. By using common sense and domain expertise, you may figure out that splitting that single feature into two could actually uncover some value that the single feature does not capture. Sometimes converting a continuous variable into a more simple categorical feature is very useful. For instance, if somebody is applying for a loan, including a very simple binary feature indicating that whether they've ever defaulted on a loan before might actually be more useful to model than a continuous feature indicating how many loans the applicant has defaulted on. Lastly, you can learn new features from existing features. One area where this is used a lot is with text data. There are algorithms like word2vec that help you learn a different, more useful representation of a word. This can be powerful, particularly for natural language processing problems. This is not a complete set of tools that can be used for feature engineering, but it covers most of the surface area and it covers everything that we'll be using in this lecture. Now let's talk about a technique that is widely used in feature engineering and it's called dimensionality reduction. There are actually a couple of ways that one can go about this. One of the things that you can do is discard features in the data. Or if it's not features in the raw data, it may be features that are synthetic features that were engineered in ways that we'll see later. But the other way that we are going to talk about is something called decomposition. The idea here is that you can apply some global mathematical technique to the entire high dimensional dataset to reduce it to fewer dimensions and yet retain most of the information content that is in it. In fact, often expose information in a way that is more amenable to modeling using the variety of models in scikit-learn or other libraries. Scikit-learn has a number of these techniques for decomposition. We'll talk later about feature reduction just by dropping features, but that's at a later stage. Here, we are interested in the ones that are called decomposition. In scikit-learn, there are quite a number of them. We are not going to talk about all. We'll talk about several of these things, but here's a list of all of them. We have things like dictionary learning, several different varieties of ICA, also several varieties of PCA, that's principal component analysis, and that's sort of the oldest one that we are going to talk about. There's also something called as LDA, NMF, and there's quite a number in here. We are not even going to go into all of them, but it's nice to read about all of these. Many of these are fairly special purpose. They deal with particular domains such as semantic textual analysis or images. Others like PCA are very general and you would apply them in any sort of domain that your dataset might occupy. And we had spoken about PCA in the previous lecture too, but we'll revisit it again. Now, as you know, principal component analysis is a widely used and fairly respected technique used for finding out what synthetic dimensions in a highly dimensional dataset contain the most information variance. That's a rather strong guarantee given when you do a PCA transformation of data. It looks at a high dimensional space, it finds out which axis that's orthogonal to everything else contains the most variation in information. This will typically or almost not be one of the features in the raw dataset that you have directly measured. Rather, it will be some linear combination of many of those features, and this dimension varies more than any other dimension you might point towards. This can often be useful before you get a first component of PCA that has the most information content in a rigorously defined way. Then you pick whatever dimension that's orthogonal to it, which is n-1, where n is the number of orthogonal dimensions, and you resolve in turn the most remaining information. The idea here is that most of the variability is accounted for by resolving a small number of dimensions in this high dimensional space. And very often, this decomposition in choosing just the first few components of a PCA will give you something of equal predictive weight as if you had used the entire raw dataset. In some cases, it's in fact more amenable to a number of modeling techniques. So, this is an enormously useful technique to use. So let's walk through this with a bit of a concrete example. We'll import the Wisconsin cancer dataset in cell 2, and this has about 30 dimensions. These are each numeric features that measure a particular medical quantity that can be diagnosed in some way. Most of these in this particular set are physical measures, the length of something or along those lines, but there are a variety in here. But in any case, they are all quantities. So we'll import it using the load breast cancer function. We'll scale it using a standard scaler. So we just want the extent of all these different dimensions to be similar. So we'll fit it using that scaler, and then we'll transform that data to get our X scaled. Now in cell 3, what we usually do, we'll take the data and split it into a training set and a testing set. Just to remind ourselves, before we try other things, let's try a couple of different classifiers against this data. So in cell 4, we'll import the linear regressor, and here we'll combine it all into one step using these chain method calls that are available in scikit-learn objects. So we'll create a linear regression object and we'll fit it and score it, all in virtually one line of code. And we find out that we get a score of about 0.72. So just keep that number in mind. We are going to use it later on. Now in cell 5, we are going to do something very similar with the k-neighbors classifier. Here we are just accepting whatever default value was, which is 5 neighbors, and we find that we actually do much better. We get a 0.95 out of that. So that's a much better predictor than the linear regressor was for this particular data and without hyperparameters. But now what we are going to do is we are going to do a transformation of this parametric space. So this is a 30-dimensional space in which these parameters exist. You can imagine 30 orthogonal vectors. So it's more than you can directly imagine, but every measurement on this is some vector in these 30 dimensions. So in cell 7, we are going to import the PCA from the decomposition submodule, and we'll do our pre-processing again, the scaling, but in particular we are doing a PCA, we are creating an object against the scaled data, and that tells us how we defined the principal components. Then we use that to transform the original data, and what we find is that in both cases we have 569 observations. But for the first we have 30 features, and for the second we just have 2 features. Let's just map those 2 dimensions in cell 9. These are not anything we can really describe in a meaningful way. They are not, for example, circumference of the tumor or color, quality or something else that is in the measurements. They are something that combines those in a way that's not necessarily intuitive at all, but it is the one that has the most information content. So looking just at those 2 dimensions, we are going to map those into a 2-dimensional parametric space where there are these odd synthetic dimensions. And in the plot, we see that we have a first principal component and we have a second principal component. The yellow and the purple are the malignant and benign tumors that were measured. And we can see even in these 2 dimensions, we get a pretty good differentiation of these things. The purple dots mostly seem to be well separated from the yellow dots. Obviously, there is some overlap here. It's not perfect, but it's a pretty nice separation simply by pulling off those 2 synthetic dimensions that have the highest degree of information. Now let's try using just those 2 dimensions in cell 10. So here we are taking the XPCA, so that's the data that has been transformed, and it's just a 2-dimensional data rather than 30-dimension data, and we'll try to do a linear regression in cell 11. We find that the linear regression does go down. So clearly for cancer diagnosis, it's not good to do this by itself as the only thing we are doing, because the reliability of that prediction is highly important. In cell 12, let's also do the k-neighbors. Here we find that k-neighbors is barely reduced at all. Of course it's reduced, so again we wouldn't want it for the same reasons, but it's interesting that the fact that we have removed 28 of these 30 dimensions barely affects the quality of the k-neighbors classifier. For the linear regressor, it has a bit more effect, but then again, the linear regressor for this particular data was not very good to start with. So it's rather interesting that 2 dimensions can do almost as much as work as the 30 dimensions. We can look at how these two synthetic dimensions, that is the principal components, are derived from these original 30 dimensions. And so in cell 13, if we take a look at the attribute of the PCA object, components underscore, we see that it is an array of 2 arrays, and the first of those is the 30 things that each have various weights, and that's the first principal component, that is taking original feature number 0, weighing that by 0.21, taking the original feature number 1, 0.103, and so on for the others. In some cases, we give negative weights to these things. So we are just doing a weighted combination of the original features in order to get these principal components. It might be easier if we do a visualization of that. So in cell 14, this visualization doesn't show all 30 features, but it just shows the first 12, just so that it represents better on the screen. But it would look very similar if we were to extend it to the additional 18 dimensions. We can see that the first component has a certain weight for mean radius, a certain weight for mean texture, a certain weight for mean perimeter, and so on. And you can see a color bar to the right side that gives us the numeric value of that particular color. This is just a prettier way to look at the textual dump of each array. And the second component is similarly weighted, but with different weights associated with each of the features in the original dataset. We won't go into it in this lecture, but there are a few other things that you may want to do in conjunction or before you do a principal component breakdown of your original features. These are the concepts of rotation, sphering, and whitening, and you should look those up. One of the things, for example, you may want to do is not look at the features themselves, but rather their z-score. How many standard deviations from the mean do they tend to vary? And that's more useful as a measure before you do PCA than looking at the original feature. But you can play around with that, and there are many academic papers on exactly what the virtues of these things are. In the next several sections, we'll move on to a variety of other decompositions that are available. PCA is probably the first one that you're gonna choose, but there are many different circumstances for other particular domains and so on, where you'll want to choose other styles of decomposition which have different algorithms underneath them and different advantages. So we looked at principal component analysis, which is the most widely used decomposition technique. But scikit-learn provides you with a number of other decompositions. We won't even talk specifically about all of them. They are quite a large number. We saw a table of all of them up above. But there are a few of them worth talking about, and we'll be going through each one of them briefly. And we'll briefly talk about some of the special areas of application of some of these other decompositions. Now, one of those decomposition techniques is non-negative matrix factorization. This works only when all of the features of the data values in your matrix are non-negative. Either your original data has to be that way, or you have to use one of the scalars that will impose non-negative values. The standard scalar that we've been using would not be suitable for this case because it centers things around 0. However, it's not really difficult using this. There's some particular domains where NMF is more effective, but in general, PCA would be the first place to reach for. One of the areas where NMF is often useful is in topic extraction. So, you have textual sources and you are doing some sort of semantic analysis on text, and NMF is a very useful technique there, perhaps even more effective than PCA in identifying the most important features. Let's look at a use of that. It's going to be very similar to doing the reduction with PCA. Here, we are not going to try to find a different data source in order to find that more effectiveness. We'll just show the API using the same cancer dataset. So much as we did with PCA, we'll import NMF from decomposition in cell 18. we'll create a NMF object with n components equal to 2. And that means we are going to have 2 dimensions. We'll apply it to the cancer dataset and we'll do a transformation using NMF and we'll take a look at those shapes. Now in cell 19, we can take a look at how effective that is in separating out things. We get something that's reasonably effective here. The picture is somewhat different than we saw with other decomposition, but we fairly get a good separation even in these 2 dimensions, where the purple dots and the yellow dots seem relatively linearly separable. Now let's take a look at how well the classifiers do in cell 20. We'll repeat the linear regression one just because we saw it before, and we'll also do a k-neighbors classification. Here we get some numbers that are a little bit less than what we saw with PCA, but basically it's in the same ballpark. So we are getting effectively the same technique and effectively the same amount of information that's retained. We may have suffered slightly in that we didn't do any scaling here. If we had scaled not using a standard scalar but one of the other scalars, we might do slightly better here. Another technique that we have for dimensionality reduction or decomposition is called LDA, latent Dirichlet allocation. The LDA creates probabilistic models for dataset. The idea is that you will do a sort of transition states between different observations and construct artificial dimensions out of that. The map is a bit more complicated, but it can be useful for certain categories of problems. Again, this is something that is often used in document processing or document or textual analysis. The way we use it again is pretty much identical to what we've seen before. In cell 21, we import it, we create an object of that class, and we specify the n components equal to 2 for this. You will see that this took a bit longer to do than some of the other techniques because it had to do the Bayesian probabilistic model. It was somewhat more computationally intensive. Now in cell 22, if we look at the decomposition, we see something a bit different. Rather than a scatter across all the 2 different dimensions, we get things kind of linearized. We still see a relatively okay separation between the values, but they are all along the diagonal. And again in cell 23, we can compare the performance of this LDA decomposition to the original values and using the 2 different classifiers. So here again, we are getting something a bit worse than what we got for PCA. Yet another one of these decompositions that's available is independent component analysis. ICA separates a multivariate signal into additive subcomponents. This is similar to PCA. It's in some sense isomorphic to it. It does the same kind of decomposition of information, but it is a different mathematical technique that's involved. There is a particular algorithm that goes into it called fast ICA that allows it to be done in reasonable time. But the typical use of ICA is somewhat different. Rather than doing the kind of decomposition into dimensions, it is often more useful for separating superimposed signals. For some technical reasons under the hood, it tends to do a better job when you might have multiple signals coming in. Those can be perhaps multidimensional signals that have been overlaid on what you are able to actually observe. But there is something kind of different going on with the 2 signals and you want to find out how these separate. One example that you often see in the literature is 2 images, 2 photographs or 2 videos that have been shown over each other. And you know that there are 2 things going on there. And you want to be able to separate out those things using the ICA technique. And to decompose them will often assist in that separation. Now you might think that these sort of target variables, this benign and malignant that we are having for the tumors, would be kind of a signal. It might be under a certain sort of physiological or medical theory that the presence of the benign or the malignant condition causes a variety of other things to occur in these measurable quantities. And so you might have the hope that when I first looked at it, that ICA would in fact be more effective than PCA. It turns out, at least in the naive way, doing this straightforwardly, it isn't that way, at least against this dataset. Maybe some additional feature processing would allow it to be, but we can see similar to what we saw in the other decompositions that we get in the two components, a reasonable visual separation. We think these are probably more or less linearly discernible. Maybe some additional feature processing would allow it to be, but we can see similar to what we saw in other decompositions, that we get in the two components a reasonable visual separation. So in cell 25, the shape of these two dimensions is a bit different. But again, the yellow dots and the purple dots are in somewhat different locations. And so, in cell 26, again we can try this with linear regression and the k neighbors. And we find something very similar to what we found with other decompositions. It's not the winner, but it's not very far off from it. And in any one of these techniques, we find that a great deal of information, the large majority of the information, is in fact isolatable into just two dimensions. Now another one of that technique which is very useful is called p-distributed stochastic neighbor embedding. Now this is a bit of technical thing and this can be used for basic decomposition. But what it's even more useful for is visualization of highly dimensional information into fewer dimensions, especially into two dimensions, which we can actually visualize effectively. It doesn't do anything particularly interesting. It gets rather low results if we try to use this decomposition against the cancer dataset. But an example that's often used to present for t-SNE is to use it against the digit dataset in cell 27. And we get a rather striking result if we do that decomposition. That, of course, was a dataset that had 64 dimensions. We can represent the image in two dimensions, height and width, and then pixel in various locations. But that's sort of not what the actual feature set is. The feature set is 64 pixels, each one of which can have a certain color value. So let's load in the digit dataset. So in cell 28, we see to remind ourselves what they look like. These are grayscale images, and so each one of them is 64 pixels position and has a certain color intensity value or gray intensity value. We can do PCA decomposition of it. It would just take a moment to do so. And we find something moderately interesting using PCA. By picking out just two synthetic dimensions of these 64 dimensions, we get something that is moderately good at separation of the different digits. There is a bit of code in that plot line. We won't exactly go through what it does. But in cell 29, the basic result is that we have in different positions in this two-dimensional space defined by first principal component and second principal component in a certain color, but then also with the digit showing itself and where that particular digit is. And we see that the 4s kind of hang right out there in the center right of the two-dimensional principal component space. The 3s are sort of a stripe along the left side, more or less. We get some zeros in the top part, and they are chiefly distinguished by the second principal components. And the 1s are sort of at the bottom right. And the others are a bit more interspersed. But it's really interesting that for the 64 dimensional data, we actually get some separation that's reasonable for in just two dimensions. And we can sort of see the clusters where the different digits occur. This isn't quite linearly separable, but it would be to some extent. So now let's come to cell 30. The thing that is really remarkable is that we try to do the same thing doing a decomposition using a t-SNE instead. Here, we'll import that and we'll do a random state of 42. It doesn't really matter, but it is what it is. But I just want you to see the same result as I see. But then we'll do a fit transform. That's where we do the fit and transform all in one step, which is one of the methods that transforms objects here. So here we are transforming the data into just those two dimensions. And now we can do the same kind of visualization as we did for PCA decomposition of the digit data. So coming to cell 31, 64 dimensions down to 2, we visualize it and we actually find a quite remarkable separation here. Each of the digits, they are so close to the cluster, it's hard to see what the digit numbers are, but you can see a bunch of 7s up here, sort of to the top left. And then there's a bunch of 6s centered at the bottom, and you get almost complete separation of the collection of each different digit. And these are very easily clusterable and linearly separable. But we can see that each of these is clustered in a way so that just distinguishing the linear regions where they will effectively occur gives us a classification of each of the digits. Therefore, we would think that these two dimensions by themselves will do quite a good job as input to a class or up higher that distinguishes the digits. So, the next section will get into this feature selection. This is where you will have a large number of features and you will want to use some of them within your later modeling. So, we had spoken about decompositions in the prior section. This is a way of just reducing dimensions or features, but in a sense, it is a specialized way. If you do a decomposition, you can decompose information into the exact same number of dimensions as you originally started with, and generally, what's done is to choose just the first few of those dimensions that retain the largest amount of information. But in principle, if you wanted to retain every bit of information in the original, you would keep the same number of dimensions. But decomposition is definitely useful. What we are going to look at now is the notion of feature selection, which is simply throwing out dimensions altogether. Not because of some transformation on them, but simply because we decide that they are not useful for our particular model. There are a number of ways that we can go about systematically deciding which of those dimensions or features we want to disregard in our particular model or in our particular process. The one that we are going to look at first is called the univariate feature selection. So, the idea here is that you compare individual features in your original dataset or your original feature sets and figure out on an individual basis which contribute the most or which contribute the least to the correlation between that particular variable and the target. We are going to focus on looking at just one of these particular functions that are available in scikit-learn. So, we are going to look at select k best. It is one that is very oftenly used. As the name sort of suggests, it wants to select the k of the variables that are available. There's something very similar called select percentile. This takes a percentage and takes, say, top 10% of the features. Obviously, when you know the number of features and you know the percentile, k is calculable from that and vice versa. So those are simply slightly different ways of expressing the same goal. There's a couple of others like select false positive rates, select false discovery rates, family-wise error. These are a little bit different, but they are the same idea of doing univariate feature selection. So we are going to look at particular features and decide whether they are the ones that we should keep or discard. So in cell 3, let's look at the API for doing a univariate selection. So here we are still looking at the Wisconsin cancer dataset. For the purpose of this particular demonstration, we are not going to use train or test, but we are going to look at the entire dataset. And indeed, whenever you do feature selection, you generally want to be operating over the entire dataset before you get to the point of separating out training and testing dataset. You want to fine-tune the dataset itself as a whole as best as possible. So here we'll import the select k best and we'll import the metric chi-squared. That's the one that's most typically used. There are a few other metrics as well, but this is what we are going to use for this purpose. This is an evaluation of the correlation, but something slightly stronger than the simple correlation between a couple of variables. So we are going to create a selector and we are making an instance of the select k object and we are using the chi-squared differentiator and we are interested in getting the 5 best features. You may recall that in the cancer dataset we had 30 features. So we are going to pick 5 out of those and hopefully those are the most informative for the model or at least most informative in the univariate way. So we can create our XNew transform data based on the selector calling the fit transform method. We could separately call the fit method and then the transform method. But here we pass in both the cancer data and the cancer target here to this fit transform or to the transformer alone, because we want to select out the same rows and the same features from both of those things. What we find here is that we modified this so that we still have our 569 rows of data as we had before, but in the original there were 30 columns or features and now there are just 5 of them. So in cell 4, let's just take a look at what those features are that were selected as being the most important. We are calling this K-best, and this is mostly just for illustration purposes. And that is the scores that are associated with different features. They are kind of arbitrary numbers and there is no intuitive meaning to the particular size of those particular numbers other than that the fact that the bigger the better. And just in order to visualize in a pretty way, we are going to use a pandas series to pour it into, and then for the index we are going to select those feature names that came from the original dataset and we are sorting it based on the data values. So that's just the most important features that are floating on the top. And we see here the 5 that were selected by the selector are worst area, mean area, worst perimeter and mean perimeter. These others below could have been selected and we would see the order in which they would have been selected if we would have used a larger K. But there is actually quite a bit of a differentiation here when I look at the rate at which the numbers descend. It seems like there is a significant drop off between the 5th and the 6th feature in terms of importances, and therefore that's a pretty good selection point. There may be a couple of other drop offs, but we are balancing where the drop offs are the steepest versus retaining enough information for the model to be effective. So let's just try out our feature selection. I expect that this is going to do worse, having thrown out some of the information in the model, but let's just see what happens. So in cell 6, we'll repeat what we have done before several times. This trend test split followed by a linear regression and k-neighbors classifier just to remind ourselves of how well they do against the entire dataset. And then in cell 7, let's try doing the same thing. Instead of using X, we are using XNew as what we are going to do the training on, and we find that we would expect that there is some reduction in the score. But it's not very much for the k-means neighbor, which is the one that we think is better anyways. I mean, it is better on the score. There's quite a bit in the linear regression because of the nature of linear regression and the fact that we are dropping features based on linear importance. You would expect more or less that you would have to go quite a way down the feature set before the information wasn't from the perspective of linear regression. But k-neighbors sort of doesn't care about that lesser important information. So in the next section, we are going to talk about other kinds of feature selection techniques. So there is another general family of selectors that are available in scikit-learn. These are selectors that are based on the model that you are actually using, or at least based on some model, even if it's not the one that you are finally going to use to model your data. This can often be more sensitive and more nuanced than using a univariate one that's based on just a single variable, because many kinds of models are able to combine the importance in some way of variety of different features or variables. There's a caveat here. We are only going to use the model-based feature selections where that particular model offers either a coefficient or a feature's importance attribute. That's not all of them, but it's quite a number of them. So you may need to select for the model-based feature selection one of those feature models that has the appropriate attribute, even if then later down the road you are going to use a different model. It still might do a better job of feature selection than simply the univariate example. The one we'll look at first does recursive feature elimination of features. The idea here is that it will do one pass through to a characterization of either the coefficient or the feature's importance, decide which is the least important, eliminate that, but then retain the entire model for everything that remains. And it may be that the thing that was of second last importance in the original training is no longer in that position with the other one removed. There can be a lot of subtle interactions, so therefore doing the recursive elimination of features is often a more powerful and accurate way of going about this. There's another one that's called select for model, and that is also available, but it doesn't do the recursive step. So in Cell 8, let's import the RFE and we'll create a linear regression as we've done before. And we'll also create an RFE object. It takes a couple of parameters when we create it. One of the things it takes in is that what estimators we are going to be using or what model that is. And in that case, we are going to use a linear regression object that we just created. As we did when we did in the univariate section, we decide to specify the number of features and the step parameter defaults to 1. You rarely have to play with this, but that's included here. And then we'll do a fit much like we do with other models or we do with a variety of things that we've learned. And we again pass in our features and our target variable. And in Cell 8 output, let's take a look at what it produces in terms of ranking of the order of the features. Of course, what this is returning is just the top 5, but it does produce an importance across all 30 features. And here we are just looking at top 10 of those. That is because we did a dot head on 10. The ones that were ranked most important are mean area, worst area, mean texture, area error, and so on. So this is in the order of importance. So in Cell 9, we can do even more here than just training the model. So we can use the RFE CV, and CV stands for cross-validate. So let's take a look at what this code does. So first, we'll import matplotlib here, and simply we are doing that because we are going to visualize the results. Then we'll import a particular classifier, so that will be random forest classifier. And as we've seen, it's a very powerful one. We import the submodule feature selection RFE-CV, and then we'll create an instance of a random forest classifier choosing max depth equal to 7, which we know happens to be a good choice for the cancer dataset. Then we'll create an instance of the RFE-CV, and then we'll fit the model against the cancer data and cancer target. Now this will eliminate one by one the least important features, but at each stage it will split the data multiple ways and do the cross-validation against it. So this in turn is even going to take longer than plain recursive elimination. Now once we have done that and we fit the recursive elimination, we can graph what is going on with it. We have some attributes that are available for this selector. One of them is grid scores and the other one is number of features. We'll make a graph that will illustrate both of those things. So we see that we get the best cross correlation we get with a certain number of features that have been selected. And so we get a very bad cross validation in result if we had selected only one feature, and it's like it's not 0ish, but it's around maybe 0.85 or something like that. But then we can see here that it quickly climbs to until 0.95 with about 7 to 8 features. But it does report to us that the actual optimum is 19. Apparently at 19, there's a peak slightly higher than the other peaks, but everything from 8 up onwards is more or less similar. It tends to level off after we've selected the most important few features, and then as we add more features, it bounces around a little bit. So one of the things to notice here is that it doesn't keep ascending monotonically past that point, and it seems to bounce around. So it may be an accident of some intricate details of that particular dataset and not that something that would be generalizable. But this general trend of rising until you hit some number of features and then plateauing is pretty typical when you use this method for feature selection. And then where within the plateau you're gonna select maybe is subject to other considerations as well, but at least you want to reach that plateau when you do the feature selection. So let's move on to feature scaling. One of the styles of feature engineering that you will almost always do in your overall pipeline of doing data processing and machine learning modeling is you will want to scale your data. Models in general respond much better to data that has sort of standardized ranges. There's a couple of aspects to that. Depending on which particular model you are looking at, those ranges can vary. Being centered at 0 and having a standard deviation of 1 is very often the way that you would like the data distributed. But in particular, this is important where the numeric ranges of different features that you have collected are dramatically different from each other. If one particular variable or feature is typically in the range of 0 to 1 and another is in the range of 1000 to a million, this can throw off many of the models. So we want to make an adjustment not by manufacturing new features or by reducing features that we think are less important, but by simply rescaling the features that exist within one particular feature so that they have sort of an expected range of values. This is a reversible transformation. We are not throwing anything out, but it makes things more amenable to our models. There are a number of these different scalars. I won't even discuss all of them, but I'll discuss sort of the most widely used ones. So let's walk through several of these different scalars that are available. These follow the same API as other tools within scikit-learn. For purposes of this particular section, we'll generate some synthetic values. We could pull data from one of our datasets and do the same thing, but we really need only a few rows and a few columns in order to understand what's going on and what are the differences between the different scaling techniques that are available. So coming to cell 2, imagine that we've created 4 columns or features and they have this various data. And you can see in the NumPy code that generates them, this particular random distributions are a little bit different and the particular ranges have a little bit of difference between these several variables. We've created 100 samples out of random number generation and so there's that 100 of each of those. In cell 3, we see that the means are fairly different between these features 0, 1, 2 and 3 and the standard deviations are a bit different. There's some other differences in their distributions. Now let's come to cell 4. It might be helpful to visualize this using a kernel density estimate. Of course, this is drawn from random number selectors, but it's strong in different ways. So generally, our expectation of where those different numbers would occur within each of these features is more or less what we would see graphed in this curve. We can see that they are centered at different points and they are spread out to different extents. We see a bit of bimodality in feature 0, which is a little bit unexpected. I wouldn't necessarily make that assumption based on the way it was generated. It's probably an artifact of the particular randomness, and also a kernel density estimate sometimes has interesting artifacts depending on the particular data. Now in cell 5, creating a histogram gives you a fairly similar picture here. This is actually binned into 300 things. We can see sort of the distribution of data here. It's pretty similar to what the KDE has done to smooth out the data. So using the sample data that we have some relatively good visualizations of the distribution and we'll try scaling it in several ways. So the first thing we'll do in cell 6, we'll use the default standard scalar and hence it's named in that manner. We'll use it in the way that we use most things within the scikit-learn API. We'll create a standard scalar object. It has some parameters that we could use, but we are not going to use it in this case, and we'll call fit transform to fit it against this particular data, and then we do some transformation. The transformation is column wise, so it doesn't look at the data globally to find our mean of the entire data or one standard deviation of the data. It looks at each column of data and finds those things for each column in turn and then normalizes based on what it finds about that column. So if we look at the raw numbers, these aren't necessarily easy to get a sense of. We see different numbers than we saw before, but the relationships are not that obvious. You may be able to see that they are sort of similar to each other than different, and in fact in cell 7, if we get a description of the data with a little bit of statistics, we find that they are still close to 1. It's been converted to a floating point by this describe, so it's showing as a floating point representation in scientific notation. The means are all not 0, but they are very close to 0, and the standard deviation you see are all close to 1. There's a little bit of jitter out there, and they are not exact, but they are approximately distributed in the same way. So if we look at our KDE in cell 8 and our histogram of that data in cell 9, we see that after this transformation, they look much more similar to each other. The KDE has a couple of artifacts. The feature 0 still has the sort of artificial bimodality that jumps out, but that's just an artifact of the random generation. But in general, they all seem to be centered around 0, and they all seem to be pretty spread out, much to the same extent. Of course, there is some difference in the distribution because they are different data series, but that's all to be expected. And we see the pretty much same thing with the histogram. Another artifact is this dataset isn't extreme enough to really show off the differences all that dramatically here, but in some cases, you will get data where most of the data is clustered around a certain value. The typical value of this measurement is 5, it might be 5, it might be 7, it might be 4, whatever, it's in a certain range, and there is some fuzz around what the typical value will be for whatever reason, and you will get a measurement of 100 or 1000 or a million, which is wholly out of the range of values that are typical of that particular feature. Now if you apply a standard scalar to that won't do so well because the standard deviation will be unreasonably large because of that one or that small number of outlier elements. If your distribution happens to be of that sort, using a robust scalar can be much more resilient to those outliers. The way it works is, it will look at quartile ranges and use those for normalization, rather than the individual data values. But we apply this in the same way as we did the standard scalar. So now let's come to cell 10 and we'll create an instance of the robust scalar and do a fit transform, and then we take a look at the data again. Just looking at the raw numbers, nothing really jumps out. So in cell 11, we see there's a little bit of difference. I mean, the means are closer to 0, but not quite close to 0 as we saw before. And the standard deviations do vary a bit more here because of the difference in algorithm. Before, the standard deviations were really close to 1, but here there are a variety of values, most of them sort of close to half, but in one case, for a different kind of distribution, significantly more than 0.69. So looking at the KDEs in cell 12, we see something kind of similar to what we had seen before. It's not quite as neatly fit, but obviously the same spread and the same center. But one of the things is that for feature 3, the thing that's noted in red, you really see a notable slant to the left. And the reason is that because the data itself initially was sort of slanting to the right, it had a long tail in the positive values, and when we use the robust scalar, the result is that sort of centering of the peak values tend to go in the other directions in order to accommodate those that were the outliers. In this case, in the positive direction, but it's not an extreme tilt, and you would call that skew in that direction. So we get something that's pretty close to normal for all of these, and even if there were much more extreme outliers, this would still do a reasonable job of scaling that we were interested in. Now looking at the histogram in cell 13, it isn't hugely informative, but we can pretty much draw the same kinds of conclusions, and we see a couple of high red bars that are a little bit to the left of 0 after this particular scaling, And that's the thing that's notable in accounting for the mild outliers that exist in the feature 3. Now, another kind of scaling that's available to us is the min-max scaler. And this just does a linear transformation on the data rather than actually normalizing it based on the standard deviation. And by default, it will put all the values between 0 and 1. We had also seen this in the previous lecture. So if you use this one, it maintains the sort of relative differences between values in a way that's more accurate, and that can be important for some models. It also allows us to use techniques such as the decomposition technique that depend on the data values being positive, because when you use this min-max scaler, it keeps all of the values within a specified range by default in the range of 0 to 1. So these, of course, then would all be positive values. So this may be useful when you have particular techniques that need all positive values, although there may be other special cases where you need all values that are within a certain range. So this may be useful when you have particular techniques that need in particular all positive values, although there may be other special cases where you need all values that are within some other range, that the numbers have to be within 5 and 10 for some particular obscure model to work correctly. And so in that case, you can use a min-max scaler to impose that particular constraint. Now in cell 14, we can see that even glancing at the numbers, indeed, these all seem to be between 0 and 1. Of course, in this case, in cell 15, we see those means will tend closer to half, being between 0 and 1 in the range of values. The standard deviations are relatively similar, but they don't need to be necessarily. It just happens that our data isn't much different between the several features. We do get some particularly interesting differences in the quartiles. The max is 1 as always, because that's what we've said for this particular scalar. In cell 16, we can again do a visualization of our KDE, and in this case, we see that feature 1 has a peak notably to the right of half, and the others are a bit more scattered in the distribution. But everything is forced between 0 and 1. You actually don't quite see that in the KDE, because the KDE mathematically extrapolates to the values beyond 0 and 1. But if you look at the histogram in cell 17, you are going to see things that are indeed narrowly constrained between 0 and 1. And every scaled data value is in that particular range. The arguments, of course, to min-max scaler would allow you to specify a different min and max if that were desirable for your purpose. So with this, we end our lecture on feature engineering.